Assalamu alaikum wa rahmatullahi wa barakatuh. Hello my students. We're gonna continue in the same chapter, chapter 8, which is DC motors and generators, part 4. Okay, so we'll start with a new section, section 8-5, the permanent magnet DC motor. For this type, we'll just take information and define this type without solving any examples. Okay, so a permanent magnet DC motors is a DC motor whose poles are made of permanent magnets. Okay, permanent magnet DC motors offer a number of benefits compared with the shunt DC motors in some applications. Since these motors do not require an external field circuit, they do not have the field circuit copper losses associated with shunt DC motor. Because no field windings are required, they can be smaller than corresponding shunt DC motor. So this type is what? Smaller than shunt DC motor. BMDC motors, permanent magnet DC motors, are especially common in smaller fractional and sub-fractional horsepower sizes, where the expense and space of a separate field circuit cannot be justified. A permanent magnet DC motor is basically the same machine as a shunt DC motor, except that the flux of this type of motor is what? Fixed. Therefore, it is not possible to control the speed of permanent magnet DC motor by what? By varying the field current flux. So the only methods of speed control available for this type is what? Are armature voltage control and armature resistance control. So we have two ways to control the speed for this type of motor: armature voltage control and armature resistance control. Let's move to the next type of motors, which is the series DC motor, section 8-6, series DC motor. A series DC motor is a DC motor whose field windings consist of relatively few turns connected in series with the armature circuit. The equivalent circuit of a series DC motor is shown in figure 6. This is figure 6, guys, here. Okay. In a series motor, the armature current, field current, and the line current are all the same, are equal, because now we are talking about the series circuit. The Kirchhoff voltage law equation for this type of motor, Vt will equal what, guys? EA plus IA multiply the summation of RA and RS, series summation of RA and RS. This is what, guys, here, just make zoom in. Okay, as you can see, this is the armature voltage, this is IA, okay, IS and IL. Okay, so the current will goes from this is power supply. Okay, we'll start from power supply. Okay, so here, as you can see, IL will equal IS will equal what? Will equal to IA. Okay, and Vt will equal what? Vt will equal EA plus IA multiply RA plus what? Plus RS in series. Okay, this is the equivalent circuit for this type. Now let us talk about what here the induced torque in a series DC motor. The terminal characteristics of a series DC motor is very different from that of a shunt motor. Okay, the basic behavior of a series DC motor is due to the fact that the flux is directly proportional to the armature current, at least until saturation is reached. As the load on the motor increases, okay, the load increases, its flux increases too. Why? As seen earlier, an increase in flux in the motor causes a decrease in its speed. The result is that a series motor has sharply dropping torque speed characteristic. Okay, has what? Sharply dropping torque speed characteristic. The induced torque in this machine is given by this equation, guys. Torque induced equal K flux IA. K constant flux multiply the armature current. The flux in this machine is directly proportional to the armature what? Current, at least until the saturation. Therefore, the flux in the machine can be given by flux equals C IA square, where C is a constant of proportionality. The induced torque of this machine is thus given by what? Okay, torque induced equal what? C IA square. C IA square. If we substitute for the flux here, for the flux, we can what? We can get what? This C equal what? IA square. Okay. Now let's move to the next slide. In other words, the torque in the motor is proportional to the square of its armature current. As a result of this relationship, it is easy to see that a series motor gives more what? Torque per ampere than any other DC motor. It is therefore used in application require what? What is the application of this type? Require very high torques. Okay. Example of such application are the what, guys, here? A starter motor in motors in cars, elevators, trains, and electric cranes and hoists. Okay. These are what? Applications of series DC motors. Now let's move to next part. The terminal characteristics of a DC motor. The resulting relationship between the series motor speed and its induced torque is, this is the relation, okay, omega equal what? Vt over K C under root K C torque induced minus what? Ra plus Rs over Kc. From this relation, we can notice that for unsaturated series motor, the speed of the motor varies as the reciprocal of square root of the torque. That is quite an usual relationship. This ideal square root characteristic is plotted in figure 7. We can just see the figure here. Next slide. One disadvantage of series motor can be seen immediately from the torque speed what relationship. When torque for the motor goes 0, when torque goes to 0, its speed goes to infinity. Okay, so when torque 0, okay, its speed what, guys? Will goes to infinity. Okay, in practice, the torque can never go entirely to 0 because of the mechanical, okay, core and stray losses that must be overcome. However, if no other load is connected, okay, to the motor, it can turn fast enough to seriously damage itself. So we can calculate never completely unloaded a series motor and never connect on to a load by a belt or other mechanism that could break. Okay, guys, we cannot we have to be careful that we cannot start the series DC motor with no load. Okay, so we have to connect with a load. Okay, as you can see from the figure here, figure 7, just zoom in. This is the torque, figure 7, torque, speed, characteristic of the series DC motor. Okay, so you have to memorize this figure here. This is the omega and the torque induced. As you can see, we have here high speed. Okay, high speed. Then it goes to approximately, okay, to the so at the starting we have high speed. So as a torque increase, increase, the speed will goes down. Okay. We'll move to the next part, guys. Here, the speed control of a series DC motor. Unlike with the shunt DC motor, there is only one efficient way to change the speed of a series DC motor. That method is to change the terminal voltage VT of the motor. If VT increases, then the speed will increase. See the first term in the torque speed equations. Okay. The speed of a series DC motor can also be controlled by insertion of a series resistor. This is the second way into the motor circuit. But this technique is very wasteful of power and is used only for intermittent period during the startup of shunt motors. However, the voltage control technique is now available with the development in power electronics. Next part, reverse the direction of rotation. This can be happened by interchanging the terminals of either what, guys, here? Number 1, armature coil. Number 2, series field coil. Okay. Note that if we interchange the terminals for both coils or the terminals of power supply, then the motor will rotate with the same direction. So we can only use one of the methods here, 1 or 2. Okay. Now we will solve one example about this type for series DC motors. Example 8-5. Okay, example 8-5. Figure 820 shows a 250 volt series DC motor with compensating winding and a total series resistance RA plus RS equal what? 0.08 ohm. Okay. The series field consists of what? 25 turns per pole, with the magnetization curve shown in figure. Okay, it will be giving for you guys the magnetization curve. Find the speed and induced torque of this motor for when its armature current is what? IA 50 ampere. Okay, so as you can see, we have the figure here down. This is the magnetization figure, and this is the what here, guys? This is the circuit giving for this example. We'll try now to solve this example. Okay, so solution here, guys. To analyze the behavior of a series motor with a saturation, pick points along the operating curve and find the torque and the speed for each point. Notice that the magnetization curve is given in units of magnetomotive force, ampere turns, versus what? EA, for a speed of what? 1200 revolution per minute. So calculated EA values must be compared to what? To the equivalent value of what? For the same speed, to determine the actual motor speed. Now the solution for IA equal what? 50 ampere. It is given from the question. Okay, we can write the equation here. EA equal what, guys? VT minus now, because we need to find EA, VT minus IA multiply RA plus RS. Okay, we have VT, which is 250 volt, minus this is IA 50 ampere, it is giving also, and multiply the resistance, the total resistance, it is giving 0.08. The answer here will be what? 246 volt. Now, since IA equal IF equal 50, okay, it is clear that IA equal what? Equal IF equal 50 ampere. So the magnetomotive force is, this is the rule by the way, guys, just memorize. Force we can find. Magnetomotive force equal what? N multiply I. What is N here? What is N? N, this is the number of turns, which is given from the question, 25 turns. I, what is I here? This is IF. Okay, IF here 50 ampere. This is the same current. The answer will be what? 1250 ampere. Okay, per turns. Now, from the magnetization curve, okay, with the same value here, okay, we can find what? EA0. EAO, it will be 80. From where we get this value, guys, here? From the magnetization curve, to get the correct speed of the motor. Okay, we can check, guys, here. Let's move to the curve here. Okay, for example here, 1200 at this point, approximately here. Just go up here. Okay, at this point, approximately it will be what, guys, here? It will be what here? 80. EA will be what? 80 volt approximately. Okay. Now we have to write this formula. This already we use this formula for shunt also. The new speed N equal EA over EAO multiply NO. Okay, we have EA from the we calculated here, which is 246, and EOO from where? From the curve, 80 volt, and this one NO from the question here, the speed 1200, guys. This is my mistake here. Okay, 1200 revolution per minute. So the speed, the answer will be what, guys? Here, this is the answer here, 3690 revolution per minute. Now we'll find the torque. To find the induced torque supplied by the motor at the speed, recall that we have this equation. Do you remember this, guys? B equal what? Torque induced multiply omega. Okay. Therefore, we can write this equation here. Okay. Torque induced equal what? EA multiply IA over what? Over omega. EA we have, which is here 246, and IA 50 ampere. And omega we have to convert it, guys, here. Okay, we have to convert from revolution per minute to rad. Okay, to rad per, okay, to radian. So we have to multiply by what, guys, here? 3690. We have to divide by what? By 60 second. Okay, 60 second, and multiply by what? 2 pi. Okay, already you know that, guys. Okay, 2 pi. So the answer will be what? The answer will be what? 31.8 Newton in meter. Okay, Newton in meter. Okay, this is the solution, the end of the solution of example of the DC series motors. Now we will solve one more example for the separately excited motor. Okay, example 8-4. Separately excited motor is shown in figure 8.1. This is the figure here, guys. Separately. Okay, the motor is initially running with VA. VA is given here 250 volt, IA 120 ampere, and the speed 1103. While supplying a constant torque load, what will the speed of this motor be if VA is reduced to what? To 100 volt. Okay, so the solutions here, we'll just make it zoom in. Okay, so the motor has an initial line current 120 ampere and armature voltage of what? 250 volt. So the internal generated voltage EA, okay, this is EA equal what, guys, here? EA equal VT minus IA multiply RA. 250 minus what? 120 multiply 0.03 RA. It is given from the question. So the answer will be what? 246.4 volt. By applying equation, okay, we have equation to and realizing that the flux is constant, the motor speed can be expressed. This is the equation. Okay, we will just okay, ignore the flux here because constant, and also the K will cancel. Okay, the constant. So we calculate the same equation here. NM2 equal what? EA2 over EA1 multiply NM1. So to find, we have to find what? EA2 using what? Kirchhoff's voltage law. So EA2 equal the same here, VT minus what? IA2 multiply RA. Okay. So guys, here just zoom in for this example. Since the torque is constant and the flux is constant, IA is constant, this yields a voltage EA2 equal what? Equal 200. Okay, 200, because this is reduced from the question, guys. Okay, reduced now. This is a new VT. We reduce the VT to be what? 200 minus what? The same IA2 will be the same 120 multiply the same RA, which is 0.03. This is the new now. The new what? EA2. One after we reduce the what here, the terminals, okay, to 200 volt. It will be 196.4 volt. Then we can what here? Apply. We can apply to find what? To find the new speed. Okay, so N now, nm2 equal what? EA2 over EA1 multiply nm1. EA2 196.4 volt over what? 246.4 multiply the speed. Okay, we already calculate. Okay, find the speed here. 1000. It is given from the question actually. The speed here in M1. 1103 revolution per minute. The answer will be what, guys? Here 879 revolution per minute. Okay. Thank you guys for watching this video, and we will see you inshallah next time for new parts inshallah ta'ala.